Okay. Today we're going to discuss an extremely interesting topic, which is to use particle swarm optimization on Ferguson Splines for smooth path planning. That's presented by me, Ashraf Faraj. The table of contents, as usual, I'm going to give an introduction, and in the introduction, I'm going to discuss why it's important to work on smooth path planning. Then I'm going to talk about Ferguson Splines, which is one of the candidates to represent this smooth path. I'll then move on to talk about particle swarm optimization, which is an evolutionary optimization algorithm. We're then going to set our fitness function to determine the path quality. Then the particle representation, which would be the final ingredient in applying the algorithm. And finally, I'm going to showcase the results on an example problem. First, an introduction. And we're just going to answer the question of why we even bother with smooth path planning. So the figure here would show a path generated by an RRT-like algorithm. It could be like an RRT star, RRT smart, or RRT star quick, or any of the variants that we previously discussed in other videos. So one of the main characteristics of this path is that it is made up of a series of line segments. So it is a piecewise linear path. So this means that we have many corners at different junctions between these line segments. Now, for a real differential drive robot who is going to move along this path, it will certainly have to stop at each point, adjust the heading, and then go on moving, which would actually mean that it would take a lot more time to run along this path in the real setting. Or the robot would still have to move quickly, but that would lead to a major problem, which is skidding or slipping of the real robot's wheels, which is quite a characteristic that happens when we have a path which has many harsh turns. And if the robot tries to follow them quickly, this would lead to skipping of the wheels. Now, why is that really a problem? Well, because this slipping of the wheel would mean that the wheel encoders would suffer many errors in counting the revolutions, so the robot would believe that it's actually moving while it's just sliding and the wheel is not turning. Now, this would lead to errors which accumulate in the odometry and would generally affect the long-term localization capability of the mobile robot. To kind of fight this problem of having really unsmooth paths, it was suggested to use kind of a smooth path to allow the robot to move on it quickly in real life situations, and this led to the idea of smooth path planning. It's usually divided into two main categories, that is the post-processing and the full path generation. Now, each has its advantages and disadvantages. So the post-processing would deal with having a path that is an output of a certain path planning algorithm, which could be an RRT, a PRM, or any other path planning algorithm, which just produces an unsmooth path. This aims to kind of process this resulting path to generate one that is smoother around the corners. Now, on the other hand, the full path generation, which we're going to focus on in this presentation, would deal with trying to find or to optimize a smooth path from scratch, that goes from start to end and that optimizes certain optimization criteria along the way. So the main advantages and disadvantages of fast processing, it's really easier to implement. It has lower complexity because it just deals with the path after it's generated. The problem is that we do not have a guarantee for path optimality. So it could be the case that the smoothing operation might increase the length of the path, might lead to intersection with other obstacles. And we really do not have that much of a guarantee, or at least, of course, not all the methods. Sure, some methods do have some kind of guarantee on the characteristics of the resulting path. But I'm saying in general, it's quite harder to include these kind of constraints in the processing process. So the full path generation method, which we're going to focus on in this presentation, has some advantages that it just produces near optimal solutions, and it has different flexible optimization criteria. So this would mean that we will have many different options to optimize while we're generating the path. And since we are dealing with this, or we are just setting this as an optimization problem, we would be able to find some really good solutions. Some of the problems, because like any other optimization algorithm, we might suffer from the local minimum. So the algorithm might just return a suboptimal solution. It's actually also quite costly and difficult to implement because we will have to cleverly choose how to represent our problem and cleverly choose how to encode the fitness function and all the other things that we're going to talk about in a minute or two. So now we're going to talk about Ferguson splines, which are one of the main methods to represent our smooth path. So a Ferguson spline P is actually a third-order polynomial curve that is defined as follows. So PFT is just a linear combination of PI F1 plus PI plus 1 F2 plus PI prime F3 plus PI plus 1 prime F4. Now T is actually a path parameter between 0 and 1. Now take note that PI plus 1, PI prime, PI plus 1 prime are actually vectors. So this means that this PT actually would be a third order polynomial in each component. Now the F1, F2, F3, F4 are actually third order polynomials defined in this method. So the actually main idea is that F1 has a value of 1 at 0 and a value of 0 at 1. Its derivatives are also 0 at both the different ends, and F2, F3, F4 are constructed in using similar kind of conditions. So now just to get a feeling of what these parameters mean, this figure right here would show us a Ferguson spline. And you can see here that the parameters bi plus 1, and the bi prime are shown on this figure. So the bi would be the first point that the Ferguson spline curve passes through. Bi plus 1 would be the second point. Bi prime would be the tangent vector to the Ferguson spline at the first point, and bi plus 1 prime would be the second tangent vector at the second point of the curve. So these parameters actually completely specify the shape of this curve by setting the start and end points and the local shape of the Ferguson spline along these starting points. Now we're going to discuss particle swarm optimization. So this is actually one of the several evolutionary optimization algorithms. So first, some terminology. A particle is actually a candidate solution. So a particle swarm optimization actually at each iteration would have different various particles, each representing a candidate solution, and it just evolves them through time based on some heuristic laws. So now each particle actually has two characteristics, a position vector that actually encodes the solution to the problem, and a velocity vector with the same dimension as the position vector, but this one just determines how the particle is actually moving at the moment in the solution space. Now we also have something called the fitness function, which measures the quality of a particle, and this tells us how good our solution is. Now the lower fitness actually means a better solution, so that's just probably the standard way of looking at things. Now the particle's motion in the solution space is mimicking the bird's swarming behavior, so that's where the name actually came from. So each particle is actually influenced by its neighbors, its best behavior so far, and its current behavior. That's how things work, and we will just look at that in more detail when we discuss the update equation of the particles' positions. So this little animation here would show us how this actually goes. We have now here several particles that are actually all spread out in the solution space, and we are seeing how they just move and converge to a certain local minima right here besides the best solution. Now we're going to discuss how particle swarm optimization works. First, we randomly initialize the particle positions, PI. and we set the initial velocity of each particle to 0, and then we repeat. We just keep repeating until the fitness function value of the best particle just stops improving and levels out. Now, the update equations we do at each time step are the following. So the velocity of the ith particle at time instant t plus 1 is actually a combination of different terms. Now, the first term is omega, a certain number between 0 and 1, multiplied by vit. So this right here means that the particle at time t plus 1 is actually influenced by the particle's previous velocity vector. So this is like kind of a momentum term, the particle just keeps rolling in the same direction it did. Now here we have C1R1 multiplied by BI best minus BIT. So BI best at time instance t is actually the best position that particle I has attained during its whole trajectory of motion. So this is like the personal best at time t. BIT is actually the position, so this right here would actually mean that the particle also tends to move towards the best position it attained during its motion. Now C1 and R1, C1 is actually a constant, it could be fixed, it could be adapted, that's out of the scope now. Now C2, R2 plus, or multiplied by, sorry, B best at time t minus BI at time t. So this right here, B best is actually the best particle found so far at time t. So this right here means that the particle also is influenced to move in the direction of the best so far. C2 is, as we said, is also a positive constant. Now R1 and R2 are actually uniform random variables. Now this helps in giving the particle swarm optimization more flexibility in exploration, in exploring the solution space. And that's how it just works. Now, I should mention that C1 and C2 are actually positive constants. They could be actually also adapted during the algorithm's run, but I'll just leave this to another time. So after I just compute the velocity, we just clip it to Vmax. So because we don't want particles to just move violently in this search space. And then we just update the position at time t plus 1 of particle I as the previous position plus the current velocity. And we just go on and just repeat this for however number of iterations it takes. So now we're going to discuss the fitness function and how do we actually set it in our problem for path planning. So let's assume we have these two obstacles, start position and the goal position are here. Let's say we have path 1 and path 2. Now, in order to be able to find an optimal path, we need to actually understand what makes a path better. So path 1 is actually shorter, but it's really dangerously close to the obstacle. So this means that if we have, we are not quite certain about the obstacle's location, then upon real execution of the algorithm, we might lead to a collision. Now, path 2 is actually way longer, but it has a safe margin away from the obstacle. So this raises the question of which path is better. So we need a quantitative measure of the quality of a certain path. Now to get there, we just need to remind ourselves of the golden goal of path planning. That is, just get to the goal in the shortest path possible while avoiding the obstacles at all costs. So to put this in quantitative terms, the fitness function must actually be proportional to the path length because we want this to be minimized, and inversely proportional to the distance from the obstacle, d. So because we want this to be, big as possible. This means we could just cook up many different candidate functions, f1 as a function of L and t could be L plus alpha on d squared. This was actually presented in reference 1, which I'm going to append in the description box. Now f2 could be just a product, L multiplied by 1 plus alpha on d. Now this is similarly found in reference 2, not exactly, but I just don't want to just come up with different fitness functions and claim they're mine because they're not. No, so the fitness function in reference 2 was actually had a similar form. It was L multiplied by some decreasing function of d. Now the third function is the interesting one. Now this I would say also not exactly found in reference 3. I just added some few stuff here. So in reference 3, it was more, there was this exponential term to, you know, to heavily penalize the distance to the obstacle. I just added this discontinuous term right here to, you know, to push all the, to push the path to have a certain distance from the obstacle. Now, this right here, M would be the margin of how much I'm actually far away from the obstacle. And the alphas in all of these are actually just positive constants. And the delta of DNM is just this kind of descriptor function. Now the final most important part is how do we represent the particles to just feed them to the PSO algorithm. So this is the final step to apply the PSO. So assume that we have two splines, F with parameters F1, F2, F1 prime, F2 prime, and Q with Q1, Q2, Q1 prime, Q2 prime. So an important question is what kind of certain conditions, you know, mathematical conditions must be satisfied at this connection point, at this joint, in order to ensure that they are smoothly connected. So basically, that just means that we need continuity and the continuity of the first derivative. So we just need that Q2 is equal to F2 and Q2 prime is equal to F2 prime. And this is actually one of the most important aspects of using Ferguson splines because they just offer this intuitive, easy kind of method or condition to connect, to interconnect splines with each other. So given that information, we now have to present the path using n Ferguson splines. We're going to treat n as being fixed in this video. Maybe later I'll try to tackle that problem of varying n to have a certain optimal selection of the number of splines. Now each particle would have the following structure. So we can see here we have a vector p0x, p0y are actually the, you know, the p1 vector that we have. We just flattened it to a row vector. So the first spline would be actually described by these 8 parameters. That's p0x, p0y, meaning the coordinates of the first point that the spline goes through. p0x and p0y prime are the tangent vector at that point. p1x, p1y is the second point. p1x prime, p1y prime is actually the tangent at that point. So now this right here would be the first spline. The second spline would share these 4 parameters with the first spline to ensure that the path is actually smooth. So the second spline would start at the same point, having the same tangent vector, which as we saw earlier ensures smoothness, and then has its own endpoint and own tangent vector. And now this just continues up and up and up until the end, until we have our n splines. Now we just have to make sure that the splines start and end at the correct points. So we just need to ensure that p0x, p0y at the start, and pnx and pny is actually the goal. We just need to make sure that this is always ensured while we're constructing the particles. Now we're going to show some of the results. We're going to test it on an example problem. This right here would show the map that we're going to test our smooth path planning on. As usual, this is the start, this is the goal, and we're trying to find a smooth, short path between the both. So we used 2 fitness functions, the F1 fitness function, where F1 was shown in a previous slide, and this actually gave us this really smooth kind of curve that avoids the obstacles and has a length of 1.5605. Now that's the result that we had using the F1 and applying the particle swarm optimization using 4 splines. Using the same number of splines with an M of 0.008, we have this. So, and we just used the fitness function 3, and this actually gave us this way smoother and not way shorter, just a little bit shorter path of 1.5518. And the most interesting idea about using this fitness function 3 is that it heavily penalizes distances to the obstacles that are shorter than this kind of M, the 0.008. So this actually pushes the distance to be as super close as possible to this M. So we just found that the D in this case, which is the distance here from this obstacle, was 0.078. So this actually gives a really neat explanation and derivation to the idea that when using F3 with a certain parameter M, we can actually nearly control the margin that the path has from the obstacles, which is really, really intuitive and interesting property. So F3, I would recommend to be quite a good choice. It just pushes D to be really close to M. We just have to make sure how to choose M so we don't really end up with some weird path cutting through the obstacles. And now I should also mention that I have used the same PSO parameters exactly for F1 and F3, so there was no difference, just to make this comparison meaningful. As we said, F3 attained a shorter path and a certain prescribed margin, which makes it probably a more favorable choice. Now, some of the final thoughts and ideas that I might try later. We might try other evolutionary optimization algorithms. Now, PSO is one of the classics. It was one of the first, probably not the first, but one of the first evolutionary algorithms alongside the genetic algorithms. They were one of the evolutionary computing algorithms that actually revolutionized the way we look at optimization. Now, there are many others. We could look at artificial bee colony. There could be the gray wolf, the firefly optimization algorithm, many different kind of variants that I could look into in the future to see how their performance actually affects the quality of the path that we can find. Now we could also use other PSO variants since it has many different variants that take into account, for example, constraints that take into account conversions that have just better conversions quality, and that could take into account many different other things. So one of those that I might try really soon would be the chaotic PSO, and this would just replace some of the randomness in the PSO update equation with random maps, with the chaotic maps, which could ensure more better convergence and better exploration to exploitation ratio. We could also try other path representations like the Bezier curves, the cubic B-splines, the NURBS, which is the non-uniform residual B-splines. I guess I'm not sure about the residual, but these are some of the other path representations that we could use that could lead to also smoother path qualities or more intuitive method of encoding the path. We could also look into the idea of optimizing the number of splines. Now, this could be a really interesting one because that would lead to something we call the variable length PSO, which deals with particles of different length, and we try to compare their qualities together. Now, this might mean that we have to add an extra term in the fitness function to penalize really lengthy paths. That's it. Thank you very much for listening. And as usual, if you have any comments, ideas, or any things you'd like me to explore more, or any different problems in robotics that you might find interesting and worth discussing, I'm more than open to the discussion and I'll be quite pleased with your feedback. And thank you very much.